Okay, we're going to talk about our last section for the week, which is spectroscopy, which is really just applied quantum mechanics. And we can't do the whole chapter. It just takes too much time, and the course really isn't long enough for that. So I'm going to do the sections on just the general aspects of spectroscopy. And then we're going to do a lab that's focused on vibrational rotational spectroscopy. And that will help give you a deeper understanding of how some of the different kinds of energy and molecules can be used to study their properties. So, okay. Okay, so the general features of spectroscopy. So this is the analysis of electromagnetic radiation emitted or absorbed or scattered by atoms or molecules. And so you've done a lot of this. You've used NMR, you've used UV-Vis in Gen Chem, you've used IR in organic. So you've already used it a lot, and hopefully this will give you a little better understanding of the quantum mechanics. So we've already talked about the Bohr frequency condition. So atoms or molecules are going to absorb or emit photons if the energy difference between the two states that are being moved between is equal to the energy of that photon. So h nu is the energy of a photon, and then the absolute value would be if you're going up or down, so energy of one state minus the other. And so we can talk about the wavelength and we can talk about wave number. So sometimes you talk about frequency, nu, sometimes you use lambda and you talk about the wavelength of light that's interacting with atoms and molecules. Oftentimes you use this thing called wave numbers, which are essentially 1 over wavelength. And you use that because 1 over wavelength is proportional to energy, just like frequency is. So most often you'll see wave numbers. So nu Natilda. So let's take a quick look at figure 1. No, the figures aren't here. Oh, there it is. Okay, so figure 1 is just the electromagnetic spectrum. And so you want to think the electromagnetic spectrum shows you the range of energies that light can have. And so depending on what the energy of the photon is, it's going to interact with different kinds of motion. So you can excite electrons to higher orbitals. You can excite a molecule to rotate with more energy, to vibrate with more energy, a combination of those. So we want to remember that the Bohr frequency condition tells us that if we know something about the light, we know something about the difference in energies. So, okay, so read section 11A.1. That's talking about different ways to set up the experiment. So different ways to build the instruments for this kind of experiment. I want to make this bigger. Oh, well, it's probably big enough. So you can either absorb or emit photons. So you can either stimulate something to go up in energy or to emit energy in the form of a photon. So we're going to first talk about theoretically what that means. So a photon can stimulate your molecule or atom to absorb energy. And the rate of that stimulated absorption is dependent on the number of molecules in the lower state, something called the Einstein coefficient of stimulated absorption. So that's something you'd have to measure. And then just the concentration or the density of the energy in that right frequency. So this would be the Bohr frequency that corresponds to the energy difference that you're trying to stimulate to absorb photons. And you could also stimulate it to emit a photon. So if your system's already in an excited state, a photon can stimulate that to give off that photon. So the equation looks the same, except now N prime would be the number of molecules in the excited state. B prime would be the Einstein coefficient of stimulated emission. And then once again, the density of the frequency of light that has the right energy to cause the transition. You also know you have spontaneous emission. So if you excite a molecule or electron in an atom to an excited state, that's going to have a finite lifetime. And just spontaneously, it's going to fall back down in energy. And so that's going to be proportional to the number of molecules in the excited state, and then another coefficient, the Einstein coefficient of spontaneous emission. So we'll call that A. So overall, the rate of emission is going to be the spontaneous emission and the stimulated emission. So we're just combining these two equations. And it can be proven that the coefficient for stimulated emission and for stimulated or for spontaneous, no, yeah, sorry. The B's, so for both emission and absorption, so B, the coefficient of stimulated absorption, and B prime for stimulated emission, that those are going to be the same. We're not going to prove that, but if that's also true, and A will then be equal to B, you can also derive this equation. So this is the coefficient for spontaneous emission, and then it's equal to 8 pi Planck's constant, the frequency of light cubed, speed of light cubed, times B, which now is going to be the coefficient for stimulated emission or absorption because they're equal to each other. So at low frequency, so if nu is small, then A is going to be smaller than B. So the rate of spontaneous emission will be less than that for absorption. So if A is then smaller relative to B, and only stimulated emission and absorption are important. So the spontaneous becomes less important. So the net rate of absorption based on that is going to be equal to the number of molecules in the lower state. So the number of molecules in the lower state, the coefficient for stimulated absorption, the density of the frequency of light, minus how much is going to be emitted. So the difference in the two will essentially be the total quantity absorbed. So this second term is how much is being stimulated to emit. And so you can just combine those and have this equation. We'll learn about the Boltzmann's distribution later, but it's a way to understand how many molecules would be in the excited state compared to another state. And so it says that the ratio of two states is equal to E to the difference in those energy states. So we can put that in here. And when we do that and rearrange the equation, we get the net rate of absorption is equal to the number of molecules in the ground state, the coefficient of stimulated absorption, the density of the frequency of light, and then this term is taking into account essentially N prime, how many molecules are going to be in the excited state. So B depends on the transition dipole moment because electromagnetic radiation interacts more if this thing is larger. So if we look at figure 6, the transition dipole moment, if you think about it, the way that light interacts with atoms and molecules is because light is an electric field and atoms and molecules can create an electric field. So this is showing you that if on the right-hand side, if the molecule has a dipole moment, then the light can interact with it because the dipole moment is a difference in electric field. And so if it doesn't, if it's a completely symmetrical molecule or atom, light won't be able to interact with that. So the magnitude of the transition dipole moment will will determine how much the intensity of light being absorbed. Okay, so we have selection rules based on that transition dipole moment. So there are two types of selection rules. So the selection rules, as we talked about in atomic spectroscopy, is just a set of rules based on the physics of the interaction of light with the molecule or atom. So a gross selection rule is the general feature of a molecule that a molecule must have if it's going to have a spectrum of a given kind. So, for example, you won't have a vibrational spectrum for a molecule if when it vibrates, its dipole moment doesn't change, because as it vibrates, that's where you're going to be putting the energy, and the electromagnetic radiation won't interact with it unless, as it makes it vibrate with more energy, it also changes its dipole moment. So we'll look here in a second at an example of that. And then a specific selection rule, and that's what changes in quantum numbers may occur. So the first one, if we look at something like carbon dioxide, if you do the symmetric stretch where each of the bonds is getting longer, the dipole moment doesn't change in that stretch. And so that's going to be a forbidden transition. Whereas if you look at another possible vibrational mode where one's getting longer and one's getting shorter, that's called the asymmetric stretch for carbon dioxide. That is changing the dipole moment as you add energy to that type of motion. And so you will see a band in the spectrum for CO2 for that vibrational transition. The specific selection rule, I think we've already talked about this one. For rotational energy, delta J has to equal plus or minus 1. So you can change rotational states 1 or 2, or either plus 1 or minus 1. So just the difference in the direction of the rotation. So that's how quantum numbers have to change. So that's a specific selection rule. And this is the properties of the molecule. So this is a gross selection rule. So that's essentially looking at the theory. Now, if we look at what you've learned experimentally, you've learned experimentally that the intensity of the light that's transmitted is related to the intensity of the light that you hit your sample with times 10 to the minus the molar absorption coefficient, the concentration of your molecules, and the path length. So that makes a lot of sense. There's some theoretical, or it's not theoretical, there is some property of your molecule that gives it a different ability to absorb. And how many molecules you have is going to determine, therefore, how much light is absorbed, as well as how many of those molecules your light's going through. So that means absorbance, which is defined as log of the intensity that you hit your sample with versus what's coming out. So just rearranging this equation, if you take this to that side and that to that side, you end up, and you can define absorbance to be the log of that ratio. And this comes out because if you rearrange this, that's what you'll get when you take the log of 10 to this set of properties. So sometimes you like to measure transmittance because it's going to be linear. So transmittance is just how much light came out versus the intensity of light you hit your sample with. And so if you look at those two equations relative to each other, absorbance can be defined in terms of transmittance as the negative log of transmittance. So you saw this in 107 and 108. And if you took analytical, you saw this in analytical. So these are just given from the equations above if you rearrange them. So stop and work self-test 11A.1 and then read through the justification. The justification just shows how the theory that comes from Beer's law matches the physics of your empirical observations. No, the empirical law is Beer's law, sorry, and from the theory of Einstein. So go back up here and think about this equation. and compare it. So that's the theory, and compare it to Beer's law. That's what the justification is going to do. So Raman spectroscopy, which I know Murphy has a Raman instrument, so some of you may have used this if you've taken his classes. It's based on the idea of scattering rather than actually absorbing. And so you have Stokes radiation, which you hit the sample with some light and it comes off at a lower frequency. That means some of the energy of the photon was used to excite the vibrational or rotational energy. Anti-Stokes is the opposite, comes off at a higher energy. So that means the molecule lost some energy in its rotation or vibration, and therefore the photon that comes off has higher energy than the light that you hit it with. So look at figure 10. Let's see what figure 10 is. That is not. Oh, this is what, oh, this is 10. So you hit your molecule with a photon, and if it comes off with a longer wavelength, that means some of the energy went to excite the molecule and not as much energy is coming off in a photon. Rayleigh is where it's just scattered and it comes off at exactly the same frequency, and anti-Stokes is where it comes off at a shorter wavelength, therefore a higher frequency, and therefore some of the energy from the molecule is added to the energy of the photon. So you hit it with a photon, the molecule loses some energy in its vibration, and so the photon that comes off has higher energy. And then want you just to look at the, so this is absorption from theory. So number of molecules, Einstein's coefficient of stimulated absorption, the density of the light that has the right frequency. And then this really takes into account how many molecules will be stimulating to emit based on Boltzmann's distribution telling you how many molecules will be in that excited state. So this second, or this last term basically is dealing with N prime. How many molecules are in the excited state, therefore how many of them might be stimulated to emit. And you can compare that to absorption from experiment, the molar absorptivity coefficient, the concentration, and the path length. And you can really compare the two and see that they have exactly the same components. So how many molecules do you have? Some property of the molecule, the absorptivity coefficient, which is similar to B. It would just have different units in how these two equations are written. So they really have the same physics in them. They just have different units. And this comes from theory, this comes from experiment, but neither one of them has some property that's not in the other one. So just to show the two equations and to show you that there are different ways of coming to the same conclusion about what predicts how much light a sample will absorb. So I think, yeah, that is it. So we are done with our first week of material.